Okay, we're back. I have uploaded the notes of what I'm about to explain, so have that printed out in front of you, and you won't have to write everything down, and I'll just explain from the notes. I realized one piece of background information is missing. For those of you who don't have much statistics background, let me explain a little bit about correlation, because we're going to need that to understand what I'm about to talk about. So let's suppose that we have some example data, and this could be, for example, the pixel values in an image that just has 2 pixels, which we often do. Or it could be, as we did in the recent example of height and weight, it could be 2 numbers like that. And then in this case, let's stick with the image example. Each image with the 2 pixels in it would be represented by a point in this diagram, because it has an x1 value and an x2 value. If I were to draw many example images of this kind, having 2 pixels, it could be that they would, I'm sort of exaggerating this, they don't even look random. I mean for this to look random. They could distribute themselves like this, for example, and that was how it was in the height-weight case. This situation corresponds to a situation where x1 and x2 are correlated with each other. So let's explain, what does that mean mathematically? Correlated means that correlated x1 and x2 means that their covariance is greater than 0. And so we need to just define covariance so we can understand what the word correlated means. So when I say that x1 and x2 are correlated, what I mean is, strictly speaking, that their covariance is greater than 0. Covariance is defined as follows. So you write the covariance of x1 and x2 is the expected value of x1 minus its expected value times the expected times x2 minus the expected value of x2. So the e's here mean expected value. If you like, you can use the word average or mean if those are more familiar to you, okay? So what does it mean for the covariance to be greater than 0? Well, here's an example where that is the case. The mean value of x1 is about here. You see this is roughly in the center, left to right of this group of points. And the mean of x2 is roughly about here. So let's make a little plus sign to indicate a point which is the expected value of x1, expected value of x2. All right. Now let's look at these example points. As you can see, typically for these particular points, if, let's look at this one. its x1 value is greater than the mean. It's to the right, this point is to the right of the average, and its x2 value is above the x2 mean. This point is above this level. And so you see that, so in these examples, so in this example, most points have the expected value of x1, have x1 being greater than the expected value of x1, and at the same time that x2 is greater than its average, so that x1 minus expected value of x1 is positive at the same time that x2 minus expected value of x2 is positive. Now that's not true for all the points. If we go back to the diagram, we see there are many points that are down here. So most points have case, let's call it case 1. Many of the points have their x1 value is below average. It's to the left of this line, and their x2 value is below average at the same time. So they have x2, x1 being less than the mean, and x2 is less than the mean at the same time. In other words, x2 minus expected value of x2 is less than 0, and I keep doing it. And x2 minus expected value of x2 is less than 0 at the same time. Now there are a few points where it's not the case, but these points dominate this overall average. And let's look at what happens if we were to average this product for all these points. Well, we have many points for which this, which is this first term, is greater than 0 at the same time that this, which is the second term, is greater than 0. So case 1 contributes to covariance being greater than 0, because a positive number times a positive number is positive. And here you have the first term of this quantity is negative at the same time that the second term is negative. Negative times a negative is a positive. So case 2 also contributes to the covariance being greater than 0. I guess we could say ditto for everything. All right. So these points, the ones that are in this quadrant and this quadrant, go opposite that, but because there's so many more of these and these, when we average it all out, we're going to get a positive number. So the covariance of x1 and x2 is greater than 0 in this example. We need to get some more paper. All right. Similarly, in this example, covariance of x1 and x2 is less than 0, so draw a bunch of points that are kind of scattered around, but where they're scattered and the tilt is down and to the right, so it's sort of a negative slope. Okay, so in that case, if we would look at the covariance, remember it's covariance this is the covariance again. In a similar fashion to before, here's the mean. Okay, and what we see is most of the time you'll have a situation of points like this where x1 is below average, so this is negative, at the same time that x2 is above average. So this is negative, this is positive. When you multiply, you get a negative. And same will happen for all of these points down here. So you'll have predominantly negative contributions, and this is negative. So here we say x1 and x2 are negatively correlated. In the previous case, where covariance was greater than 0, we simply said correlated. We could have said positively correlated, but usually when you leave off the word positive, people understand that that's what you really mean. Okay, so final case. Here's x1, here's x2, and now let's imagine that the points lie in an elliptical region that is not tilted. So you have, again, the mean is here, but there's no tilt. And so in the four quadrants, because of the way the symmetry here, when you do these products, you're going to get some points are going to contribute positively, some are going to contribute negatively, and so on, but it's going to all cancel out on average. And here the covariance is 0. And we say x1 and x2 are uncorrelated. All right, so it's important to understand those quantities, these statistical quantities, because that is going to figure into our compression ideas and this idea of redundancy. So when the covariance is 0, this means that the data lie in a pattern that's not tilted, basically, and where knowing the value of x1 for one of the points doesn't tell us any information about the value of x2. Now, this is what I just said. Is not very strictly right. For it to really have no information whatsoever, we'd have to say that the two are independent. That's an even stronger statistical statement. But for our purposes, let's simplify and just talk about correlatedness. If the data are Gaussian, then saying they are uncorrelated is the same as saying they're independent. Okay, so in a situation like this, no compression can be gained by use of the correlations. Here, compression could be gained because from one of the numbers you could guess the other number. If you know x1, you could make at least a guess at x2. So an example like this would be two things that would be negatively correlated would be, I don't know, the temperature and the number of not temperature, pardon me, the amount of rain in the weather, and no, that's a bad example, sorry. Let's do temperature and the number of people wearing heavy coats. So when the temperature is high, the number of coats is low. When the temperature is low, the number of coats is high. And when I say high and low, I mean with respect to the average. So when one's above average, the other's below average, and vice versa. And that's a negative correlation. Okay. So now let's go to the notes. So we've already introduced this. This is the method that I explained in the slides. And now what I want to do is to derive the method that I described in the slides. I guess we don't need to review this stuff. This is more or less what I was just saying a moment ago, but you can read it again. Okay. So before we launch into the derivation, let me go back and put everything in context for a moment. So what we're focusing on right now is spatial redundancy in image compression. And the first method we learned was differential pulse code modulation, or predictive coding, where you would try from one pixel to the next or one block of pixels to the next to predict what those are going to be. And now we're learning this other trick, the KL transform, or principal component analysis is a different name for it. And the idea of this one, remember, is that we're going to describe the pixels by a series expansion, and then instead of using the pixel values to communicate the image, we'll use the series expansion coefficients to communicate the image. And we're going to come up with a series expansion which makes it very efficient to do the communication, where if we only use the first few terms in the expansion, we'll actually get a very, very close to describing the image. And that saves us from having to transmit all the individual pixels. And probably it's good to keep this graphic in your mind as you think about that. Remember, this is the idea that you can construct a picture of the letter A by adding together these cosine basis images, which are the terms in an expansion. And as you add terms, the image looks more and more like an A, and it does that with far fewer terms or coefficients than there are pixels. So this image had 64 pixels in it, but maybe, 30 or 40 coefficients would be enough to get you at least a decent representation of the picture, if not perfect. Okay, so we're going to learn the math of how we would ideally do this representation. And this is the Carhoon-Loewe transform. So we're going to represent our image as a sum of these basis images. These are unit vectors that describe those little basis images. And these are the coefficients that are needed to multiply these by, so that when you add them up, you'll get the image. So if you were to do this like with the letter A, this would be 64. You'd have 64 pixels. And the question that we pose here mathematically is, well, how can I choose these basis vectors in such a way that if I would represent x in this approximation, so this is an approximation for x, that I will do as good as possible. Now, what's the difference between this one and this one? The only difference is that I only sum up to m, and m is less than n. So that's this situation I just described. To do it perfectly, I need to add these, all 64 of these cosine functions together in the right amounts to exactly make the letter A. But if I add, maybe this many together, all of them up to here, it looks pretty good. So the question is, what should those basis images be to make that possible? And remember that we don't usually think about it this way, but when we are talking about images normally, or really any vectors or arrays, the basis that we're using, the basis images, are ones that look like this. So that would be the first basis image. That's the second basis image, right? When we say a certain image has a pixel value of 5 here, what we mean is you take the number 5 and multiply it by this basis image, and then you add this basis image multiplied by whatever the pixel value is here. And that's the process mathematically that you are really using to build up the image. But that's very inefficient because you're filling one pixel in at a time, whereas those cosine type functions I showed you a minute ago fill the image up completely with every term. All right. So the goal is to figure out what would be good basis images instead of our usual ones. Well, like we have done in the past, when we say we want to find the best of something, remember when we did least squares, we would say the best image in a least squares sense, for example. So here what we're going to use for best is the mean square error. So it means how wrong will we be if we only use less terms, m terms. So that would be like saying, okay, if I stop here, I only send the coefficients, all of these up to here, so this would be x hat, and this would be x, and you could say, well, how bad is that? And the way we're measuring that is the average of the length of the difference. So that really means we subtract the two, square all the pixels and add them up, and then find the average. All right, so that's the quantity we want to minimize. And all I'm doing in these following steps is to get this error in terms of these basis vectors. These are what we really want to find out, is what vectors should we use for this kind of coding scheme we're going to derive. So this is the thing we want to minimize. It's this error. Now, we know we want the phi's, these basis images, to be orthogonal and be unit vectors, to be a helpful basis. And the reason we want them to be orthogonal is that this will definitely avoid any redundancies. So orthogonal means that the dot product of the two images is of any two different basis images is 0. The dot product of a basis image with itself, so if I is equals to j here, it's 1. That simply means it's a unit vector. The more important thing is you want any two basis images to have a dot product of 0. That essentially means that there won't be any redundancy caused by the basis. So let's imagine that I had a coordinate system where the vectors were not orthogonal. So I'm deliberately drawing these so that they're not a right angle here like we would usually have. So let's say this would be like x1 and this would be x2. Well, in our notation, let's be precise, it would be y1 and y2. If we did it like that, then even before we begin, we're going to have redundancy, because if I know the y1 value of something, that tells me something about the y2 value. That's no good. We want to have these to be perpendicular, because now if I tell you y1 is this, that doesn't tell me anything about y2. Okay, so we want to minimize this. We know we want to have this condition. If these are orthonormal, then this is just a delta, a Kronecker delta, and this equation simplifies to this. So it simply means that the error that we'll get when we only have m terms, that means the error we'll get when we stop and settle for this image instead of the perfect image, will be the sum of the squares of the coefficients y of the terms that we've left out, the ones that are not included in the communication. So remember, the full image you have to sum from 1 to 64 in our example. Here we're only summing from 1 to, let's say, 40. This is saying here that the error is the sum from 41 up to 64. So if you want to put example numbers, you could. Okay. So that's the thing we want to minimize. Now the coefficients in this series expansion are just, when you have any coordinate system, you find the coordinates or coefficients by simply doing the dot product of the point onto the basis. So if I would have, here's phi 1 direction and phi 2 direction. So let me do it like this, and then that would be y1 coordinate, y2 coordinate. If I'd have some point x, I would find the y1 and y2 by dropping the perpendiculars here and here, and that's the same as taking the vector x and doing the dot product onto this vector or that vector because they're unit vectors. Okay, so in that case, I'm here substituting. So here we found out that this error that we want to minimize to make this work as well as possible is this guy. It has y here, that's the coefficients, but we just realized those are just dot products, so we plug the dot products in here. And then I expand out the square. Then I know that the expected value is linear and it can be commuted with these other multiplications. So I can bring the average in here because these are not random, only the x's are random. And this leaves me with what's called the correlation matrix of x. This is the dot product of x, the outer product of x and x, so xx transpose. Now, I'm sorry, this is a bit confusing. So let's assume now, for simplicity, that our images have a mean of 0. So that would be like, remember in our height and weight example, I did a step where I mean corrected so that the mean was here. Okay, in that case, then you'll notice that this bears a resemblance to this. Okay. So this is a matrix where each entry is the expected value of a product. So the 1, 1 element of the matrix is expected value of x1 times x1. Then this is x1, x2, and this one is x2, x1. But of course that's the same. And then x2, x2. Okay? Now if the means are 0, the means of x1 and x2 are 0, that's identical to this, right? If this mean is 0 and that mean is 0, all I have in here is x1 and x2. So this is the covariances, or covariance matrix, if expected value of x1 equals expected value of x2 equals 0. Uh-oh, sorry, I'm writing off the page. I'm sorry, I just noticed that, so let me go back. So what I'm doing is diving into this matrix and understanding what is it. Its elements are expected value of products of the pixel values. Now, I'm talking about I'm again here doing a simple example where there are only 2. In a real image, there would be, in our example, 64. This matrix would be 64 by 64. And each element, if the means of the pixels are 0, is essentially these covariances that I talked about a second ago. Okay. Now, the goal is to find the basis images, these vectors, that minimize the error, that make our coding as efficient as possible. So we have the least amount of error if we only use M terms, subject to the orthonormality of the images, the basis images. So we know our trick for doing this is really a constrained optimization. I'm going to minimize this, subject to this being 0. So that's like the constraint term that we learned in Lagrange multipliers. And because we want this to be true for all of them, we're going to have a multiplier for every one. And I won't spend a lot of time on the details here. I'm doing all this really just to motivate it. Mainly I want you to understand the final answer and how to use it. So to minimize the error while keeping these normalized, we would take the derivative and set it to 0 like we used to do. Remember the problem of a cardboard box or the least squares, constrained least squares. Take the derivative, set it to 0, and solve. If we do that, we aren't able to solve explicitly for the phi's. You can't isolate the phi's that you're trying to find out, but you can discover that they obey this relationship, and this is an eigenvector equation. Okay. So it turns out that the best basis vectors are the ones that are the eigenvectors of the correlation matrix. Or if the means are 0, that's the same as saying eigenvectors of the covariance matrix. Let me try to put that in a little bit of perspective. This is a bit of linear algebra stuff that you may not know, but let me try to at least give you an idea about it so you can see what's going on. So let's suppose that I have 2 pixels, so I can draw it, and these are each point represents an image that has 2 pixels, and these are like typical images, let's say. Okay. We know from before that this situation refers to one where these have a covariance that's positive, right? It's tilted, and we talked about that earlier in this lecture. If I were to define the covariance matrix of this, I would have a matrix which is something that has the expected value of x1 squared, expected value of x2 squared, expected value of x1, x2, expected value of x1, x2. This would be greater than 0, and this would be greater than 0, because this is a positively correlated situation here. Okay, so if I actually compute this, what I will find is that solutions will have phi 1 going this way and phi 2 going this way. If these are Gaussian and fall in a region that's sort of an elliptical shape. The eigenvectors, phi will be the major and minor axes of this ellipse. That's just a fact of linear algebra that we won't go into, but I want you to know that that's the case. That if I would go and measure for all of these points, find the average of x1 squared. So I'd find the value of x1 for all of these guys and find the average square of that. Do the same for x2. Find the average product of x1 and x2, which I'd find to be positive in this particular case. If I make that matrix, so now think you're doing it on the computer in MATLAB, I'll just get a little 2x2 matrix. If I find the eigenvectors of it, they will be the major and minor axes of the ellipse. Okay. All right. Now, the question is, we know that they're the major and minor axes, but what we don't know is which axis is the one, or which axes are the ones to not use. So coming back to here, let's suppose I did this eigenvector analysis on a bunch of images, 64 by 64 images, and let's say I found that all these guys, all these images are those basis vectors. And the question is, how would I know? I mean, I've arranged them in an order here to imply that I know I should use this one first and then this one and so on. But if I would do this in MATLAB and just do the eigenvectors, I don't know which order they go in to know, oh, I should add them in a certain order and then stop and then just not use any of these bottom ones. The question is, how do I know which ones to use? And the answer comes out of this math. The error, remember this error, is the error between my smudgy approximate image and the perfect image. It turns out, after a few steps of math, is equal to the sum of the eigenvalues corresponding to the terms that I don't include, the omitted terms. You see, it's a sum. So for my example, this would be from 41 up to 64. So those are the ones that contribute to the error. So if I want to have the smallest error possible, naturally I want to choose to omit the terms where lambda is a small number, because those are the ones that go in the sum. So this means I should keep the terms whose basis vectors have the biggest eigenvalues. Okay. So this semester, because we've had a lot more students with less background, I've tended to skip some of these long derivations. I'm not going to discuss this one right now. If you're interested, you can read it. But all this is saying is that if I represent a vector instead of using the original ordinary basis vectors, the ones that we're familiar with, if I instead use these eigenvector directions as our basis, really all I'm doing is rotating the coordinate system, you see. The new coordinates, y1 and y2, like this. And this should look familiar from my example with height and weight, remember? This was, I've forgotten which was which, maybe height and weight. Y1 was what I called size, and y2 is what I called proportions. And you see that after this rotation, y1 and y2 are now uncorrelated. Remember, uncorrelated from earlier in this lecture was the situation where the points fell in a pattern that was not tilted. And you can see that if I use y1 and y2 as my coordinate axes, in terms of them, the grouping is not tilted. It's tilted with respect to the original pixels, but not the new coordinates. So those are uncorrelated. So what that means is, let's think back to redundancy. The reason that we want to do this is we think that x1 and x2, 2 pixels, are correlated with each other, and therefore there's redundancy. If I know x1, I have a good chance of guessing x2 in this situation. But once I re-represent the image in terms of y1 and y2, if I were to communicate y1, it now tells me nothing about y2. So that makes sense. It's compact. Each one is uncorrelated and uncoupled from the other. And this is simply a proof of that. Okay, so let's do a very specific example together. So let's say I have 2 pixels, x1 and x2, or these could be height and weight or something. And let's say that the correlation matrix looks like this. So remember, these ones were the covariances. And let's assume means equals 0. That is, assume that the average of x1 values and average of x2 values is the same. Sorry, same and 0. Okay. 2 here simply represents that x1 has a greater variance or standard deviation than x2 has. So it's more spread out. Well, I didn't draw it very well there, but it's more spread out along x1. Okay. If I do the eigenvector calculation, and when a matrix is 2 by 2, if you've had a linear algebra class, you'll know that you can actually calculate the eigenvectors and eigenvalues by hand, by simple algebra. But I did this in MATLAB. I got 2 vectors. So each of these, so these guys are, well, I'm not sure if I should number them yet. But let's go ahead and do it. So these constitute the phi 1, and these constitute phi 2. This is lambda 1 here. This is lambda 2 here. These are the eigenvalues. All right, so now let's try it on an example data point. So remember, this is like the height and weight problem where I looked at one individual person and I said, okay, you know, if I leave out either the height or the weight, we're going to be way off in describing the person. But if I leave out the proportions variable, that rotated thing, then I won't be too bad. So that's the kind of thing I'm going to illustrate numerically here. So let's say there's a specific example, person or example 2-pixel image with these values. So I made this up randomly. And let's find out what are the coordinates in the new y coordinate system. So this is y1, this is y2, this is x1, this is x2. So what I'm saying is, if I only tell you one coordinate or coefficient, if I only transmit y1, that's this number here. It's a little bit grayed out, but that's this number here. Then the question is, how wrong will I be? Well, what I'm saying is I do a series expansion to make my approximate x by taking y1 and multiplying it by phi1. The whole series expansion, if I would use all two terms, there are only two terms here, would be y1 phi1 plus y2 phi2. But here I'm stopping the series with just one term, so I just have y1 phi1. And when I multiply this out, I get that. Now the question is, how close is that to x? So this is x hat, and x is that. And looking at it, we can see already it's not too bad. Let's draw it. This phi1 direction, good point here. This phi1 direction is saying that the y1 axis is in a direction that's minus 0.85 this way, and then minus 0.5 down. Okay, so that defines this direction here. And if I could use inverse tangent to work out what angle that is, and I would find that it's 31.7 degrees here. Okay. So if I use that funny rotated coordinate system, I see that I have, if I go out, if I'm doing is I'm describing my little image or person as being this far along the y1 direction. Boom. So this is, that is 2.3539, and I'm not going anywhere in the y2 direction. I've eliminated that one. That's where I'm getting my savings in compression. And you see that puts me here. The correct answer is here. So you see, indeed, that was a very good approximation of the truth. So x hat is a good approximation of x. Excuse me. My throat's getting a little sore. Okay, so let's look at how we did with our error. Remember the equation was the average error, not the error you get every single instance, but if you do it on average over many images, it's the sum of the eigenvalues of the corresponding to the phi's that you don't use. So the one we did not use is number 2. And that eigenvalue, number 2, was this one. The second eigenvalue was 0.382. So the average error the average squared error we would have, so this is average squared, so it's the mean or average squared error, is 3.382. Well, in our one specific example, remember what this means is it's the average squared error. In our case, we just have one example, but let's see if it's close to the average. Well, x, the data we were trying to represent was this. The approximate version we got by just using the coefficient y1 alone to represent the data was this. If I subtract and then do the square norm, I get 0.31, which is close to the average of 0.382. Now, let's suppose we were dumb, and instead of throwing away, so turns out y1 points this way. Oops, no. I think I had it pointing that way. That's the same thing. y1 points this way, y2 points that way. If I had thrown away the long axis instead of the short axis, if I had made a mistake, I would have tried to compress by using only the second component of it. I would have gotten this as being my value, and if I find the error there, I would have gotten 2.93, which is much worse than 0.31. So indeed, it was what we did was the smart thing to do. Okay, so I know that was a bit abstract compared to a lot of what we've done. I wanted to expose you to that idea because it comes up so much in image processing. And it's a useful tool in pattern recognition and things. Well, that idea motivates one of the most important parts of the JPEG algorithm. And I think what I'll do here is stop the recording and then continue in the next video.